Hello everyone, I'm really excited to be here to present our work in contact mode guided sampling-based planning for quasistatic dexterous manipulation. So in this paper, we propose a sampling-based planning framework that solves dexterous manipulation problems with either no pre-specified contact sequence or predefined manipulation skill. Basically, we only need to tell the planner what are the start and goals, and the planner will do the rest for us. So yeah, I'll show that our framework is really simple but quite effective. To start, let's look at some example of dexterous manipulation and why generating motions for it is really hard. So here is a video of human dexterous grasping in a convenience store. We can see that it involves interactions with the environment and many discrete changes of contact. So it's really hard to formalize such interactions and even harder to plan for contacts. And we can also see that dexterous manipulation is really versatile and task and environment dependent. People have came up with a lot of dexterous manipulation skills, such as pushing, pivoting, and rolling, shallow depths insertion, but it's not practical to have a library of these skills and stitching them together because dexterous manipulation is so task and environment dependent. So what we want is a more general way to generate such motions. Our key idea is to use contact mode. And next, I want to show that our planner is contact mode is really simple, but really effective in generating such motions. Our problem formulation, the input is going to be the start and goal configuration of the objects. And we know the properties of the object and the environment, including their shapes and the friction coefficient. And we assume a simple model for the manipulators. They are just n free-flying space balls. And the object is allowed to interact with both the hand and the environment. The output is going to be a sequence of object configurations and a sequence of contacts. We also made the assumptions of everything should be rigid body and every motion should be in quasistatic. So what are contact modes? Contact mode is a natural way to describe discrete changes or discrete transitions of contact. So here is an example. So these two red dots are contacts. If the object is sliding to the left, the contact mode is going to be left slide, left slide. If the object is pivoting at this point, the contact mode is going to be separate and fixed. So a contact mode describes all the relative motions of all the contacts in the system. And the set of feasible contact modes enumerate all possible transitions of the states of contact. And our previous work found something very interesting and very nice about contact modes is for a single object, contact mode enumeration is O n log n in 2D. So the n is the number of contacts and it's still polynomial to n in 3D. So this really makes contact mode enumeration feasible in our framework. And once we have a contact mode, given a desired object velocity, we can find the closest feasible object velocity under this contact mode by solving a quadratic programming. So we, under these contact mode constraints for velocities and forces, and also the quasistatic assumptions. And this QP is really fast to solve. So now we have the velocity. Given the start and goal of object configuration, we can also find the closest object configuration by numerically integrating the best velocity found by this QP with first order errorless method. Yeah, this is how contact guide the motion generation. And this numerical integration process is shown here. We have a start configuration, and this is the visualization. And all reachable configuration under a contact mode is included in this manifold with boundary drawn with those blue lines here. At every time step, we can solve the QP and integrate the best velocity we get. So at each time step, we can walk towards the goal configuration. And here are two examples of we have the goal configurations, and here are their closest configurations on the manifold computed by this numerical integration process. And we can see that enumerated contact modes are just like motion primitives. They all constrain motion to be on a lower level manifold. The difference is that we don't need to spend any effort to pre-design anything. And contact modes also help generate more varied motion because they cover all possible contact transitions than motion primitives. And integrating them into an RT is pretty easy. So basically, we just like for randomly sampled configuration, we find it's Q near, X near, and for every X near, we enumerate the contact modes, and for every feasible contact mode, we try to extend to the X random, which is just the contact mode guidance numerical integration process. And we can also try to relocate manipulator contacts at random, or if the motion is not feasible, or if the finger contacts collide with the environment. The relocation is based on rejection sampling, so it's easy to incorporate different hand models. And the relocation is successful if static equilibrium can still be maintained with the remaining contacts. Yeah, we can see that this process ensures solutions to be found on zero volume manifold in a configuration space. Like this left slide motion, the possibility of being sampled is 0. And for this motion, it's the possibility of being sampled is even 0 for constrained planning, where people project the configuration onto contact manifold instead of contact mode manifold. And it's quite effective to explore both the discrete and continuous spaces. And here are our test tasks in 2D, and the settings are really diverse. The task limitations constrain them so that they all need some extent of dexterity. Yeah, and the blade cannot be directly picked up, so we need some maneuvers like this. Yeah, we can see that it has different strategies for different objects, object shapes. And in this, we can see that this planner can plan a lot of contact changes. This is in hand manipulation, and this blue block is the palm, and it uses the palm to reorient the object. It also works for planar pushing. Yeah, we also you execute our plan using a hybrid force velocity controller. This is the push the block up to a cliff, and this is the obstacle course. Yeah, we can see that dexterous manipulation can be achieved by a really, really simple manipulator. Yeah, and here are the planning statistics. For most tasks, the plan can be generated within a few seconds, and with small numbers of tree node, and it can plan many contact changes in the path. So a good news is that this planner also works in 3D. So here is our most recent results. We can see that for 3D, the applications are much more. Yeah, we can also allow user-defined manipulator models. So here's a parallel jaw gripper. And surprisingly, it really matches the strategy in human manipulation. And if you are interested in our 3D formulation, please check out our paper, Contact Mode Guided Motion Planning for Dexterous Manipulation, and it's on archive now. It also works well for object reorientation tasks, which it is not specifically designed for. So in conclusion, we propose a contact mode guided sampling-based planner for dexterous manipulation, and our method is simple, general, and fast for various manipulation tasks. Thank you.